Okay, here we are with Chapter 8, Video 2, Rotational Inertia. Make sure you've got your notebook ready for some notes. Pause the video as you need to, rewind, and let's get to it. So just as an object at rest tends to stay at rest, and an object in motion tends to remain moving in a straight line, an object rotating about an axis tends to remain rotating about the same axis unless interfered with by some external influence. The property of an object to resist changes in its rotational state of motion is called rotational inertia. Bodies that are rotating tend to remain rotating, while non-rotating bodies tend to remain non-rotating. In the absence of outside influences, a rotating top keeps rotating, while a top at rest remains at rest. This rotational inertia is sometimes also called moment of inertia. Like inertia for linear motion, rotational inertia depends on mass. The thick stone that rotates beneath a potter's wheel, for example, is very massive, and once it starts spinning, it tends to remain spinning. But unlike linear motion, rotational inertia depends on the distribution of the mass about the axis of rotation. The greater the distance between an object's mass concentration and the axis, the greater the rotational inertia. For example, in this diagram here, we see that the mass distribution in the one on the left is more concentrated to the axis of rotation. This line indicates the axis of rotation. This mass distribution, the mass is distributed further away from that axis of rotation. This side over here would be more difficult to rotate than this side over here. Now, the greater the rotational inertia of an object, the greater the difficulty in changing its rotational state. This fact is used by a tightrope walker who carries a long pole to aid in balance. Much of the mass of the pole is far away from the axis of rotation at its midpoint right here. The pole, therefore, has a whole bunch of rotational inertia. If the tightrope walker starts to topple over, a tight grip on the pole rotates the pole. But the rotational inertia of the pole resists, giving the tightrope walker time to adjust their balance. The longer the pole, the better, and better still if masses are attached at the ends of the pole. But a tightrope walker with no pole can at least extend their arms at full length to increase the body's rotational inertia. The rotational inertia of the tight walker's pole, or of any object now, depends on the axis about which it rotates. So that's three things that rotational inertia depends on: the mass of the object, the distribution of that mass, and the axis about which that object rotates, or the axis of rotation. Let's think about this axis of rotation for a minute. So look at this pencil here, right? There's three axes of rotation that this pencil could have. First, it could rotate around its central core parallel to the length of the pencil, so the pencil would rotate this direction. Second would be about its perpendicular midpoint, so that the pencil would rotate around this direction. And third, it could rotate about an axis perpendicular to one of its ends, so it would be able to rotate, say, this way, okay? So here are all three of those possible axes of rotation. Now, the rotational inertia is really small around this first position. It's easy to rotate that pencil between your fingertips because most all the mass is very close to the axis. We're talking about the mass is distributed in the thickness of the pencil. Around the second axis, like that used by the tightrope walker, the rotational inertia is a little bit greater. And about the third axis, the end of the pencil, so that it swings kind of like a pendulum, the rotational inertia is greater still because of that distribution of the mass. We can see how rotational inertia comes into play in baseball, okay? There's a long baseball bat, when it's held near its end, has more rotational inertia than a short bat. Once it's swinging, it has a greater tendency to keep swinging so you'd be able to follow through easier, but it's harder to bring it up to speed. So that's why when kids are learning to play baseball, they may be told to choke up on the bat a little bit because it shortens the length of the bat from that axis of rotation, makes it easier to bring up to speed. A short bat with less rotational inertia is easier to swing. Rotational inertia also explains why a long-legged person tends to walk with slower strides than a person with short legs. The different strides of animals with different leg lengths really show this. Giraffes and horses and ostriches run with a slower gait than dachshunds, mice, and bugs. Now, it's because of rotational inertia that if I take a solid cylinder and a hollow cylinder, start them from rest and let them roll down an incline, the solid cylinder will roll down that incline faster than the hoop. Both rotate about a central axis, and the shape that has most of its mass far from its axis is the hoop. So, for its weight, a hoop has more rotational inertia and is harder to start rolling. Any solid cylinder will outroll any hoop on the same incline, regardless if they have the same mass or outer diameter. Now, this doesn't seem plausible at first, but remember that any two objects, regardless of their mass, will fall together when dropped. They will also slide together when released on an inclined plane. When rotation is introduced, the object with the larger rotational inertia relative to its own mass has the greater resistance to a change in its motion. So, any solid cylinder will roll down an incline with more acceleration than any hollow cylinder, regardless of mass or radius. A hollow cylinder has more laziness per mass, you could say, than a solid cylinder. This figure here compares rotational inertias for various shapes and axes, and you should take a moment to pause the video and take a look at each of these. Make sure you make note of them. We'll take a look at examples of these types of rotations in class, as well as several others. See you then.